Hey everybody. Today we're talking about exponential functions. Let's start just by talking about the laws of exponents. These are going to be important through the whole conversation. So first of all, if you are multiplying two things that have the same base, you can just add the exponents. Similarly, if you're dividing two things with the same base, you can subtract the exponents. And if you have a base to an exponent to another exponent, you can multiply those exponents. Notice the parentheses. B to the x is inside a parenthesis, so it's not just the x being raised to the y, it's the b to the x being raised to the y. If you have a product to a power, you can take the power of each of the factors and then multiply. Finally, if you have a negative exponent, you can take a reciprocal before you apply the exponent. One other thing to bear in mind is if you have a fractional exponent, it's talking about a root. So b to the 1 over n is the nth root of b. Let's do a couple of practice problems with those. 2 times a to the third times b to the sixth, all taken to the fifth power. So first I'm going to apply that fifth power to each of those three factors. 2 to the fifth times a to the third to the fifth times b to the sixth to the fifth. Then I'm going to use the property of exponents to think of a to the third to the fifth as a to the 15th, and b to the 6th to the 5th as b to the 30th. Finally, let's use the fact that 2 to the 5th is 32 to get our final answer. Problem 2. 4x to the 3rd, y to the 4th, times 5x to the 5th times y. So this is all being multiplied. I can multiply in any order. So I'm going to do 4 times 5 is 20. X to the 3rd times x to the 5th is x to the 8th. And y to the 4th times y is y to the 5th. So remember that y can be written as y to the 1st. So that's how I'm getting that 5th power. Finally, 3x to the 8th over y to the 6th to the negative 2nd. So the negative power is going to flip everything over, and then the second power is going to distribute to each of those individual factors. So for example, the y to the 6th in the denominator gets moved to the numerator by that negative exponent, and then when I square it, I get y to the 12th. Overall, y to the 12th over 9x to the 16th. We're ready to define an exponential function. It's one that looks like this. The real key thing here is that the exponent is the variable. X is in the exponent, not in the base. B, the base, has to be a positive constant, can't be equal to 1. If b were equal to 1, the function would just be constant. It would be 1. So it won't really do to call that an exponential function. If x is a positive integer, this is super easy to evaluate. Then the exponent is just doing repeated multiplication. Things aren't really any worse if it's a negative integer because you're doing that repeated multiplication just in a denominator. Finally, if x is a rational number, so a fraction, we can use the fact that when we do b to the 1 over q, it's the qth root of b, to get the answer. So b to the p over q will be the pth power of b, then take the qth root of that. So all that's really left is if the exponent is an irrational number, like the square root of 3 or something. And we can fill in those gaps using limits. We won't go through that whole process here. Instead, let's look at the graphs. So y equals b to the x is going to look different depending on whether b is between 0 and 1 or greater than 1. If b is greater than 1, you get exponential growth. The function's increasing, and it increases fast once x gets to be bigger than 0. Similarly, if b is between 0 and 1, you get exponential decay. The function decays very quickly, especially when x is negative. Of course, b cannot be negative in this situation just by definition. The domain of any exponential function is going to be all real numbers. No matter what b is, we can plug in any number we like for x and get a value back. The range is going to be all positive numbers. B is positive, so no matter what exponent I use, I'm going to get a positive number back. The domain and range are also very clear from the graphs. Every x value in each of these graphs has a corresponding y value. The domain's all real numbers. The positive y values have corresponding x values. The negative y values do not, so the range is only the positive real numbers. Let's wrap up this video by doing one more problem. So here's a picture of a graph. It's going to be an exponential function, but with a constant multiple in front. it's going to have the form f of x equals c times b to the x. We're given 2 points on the graph. We need to find what c and b are. By the way, we should expect that b is going to be between 0 and 1, because here we're seeing a picture of exponential decay. So we're going to plug in the 2 points that we have and get 2 equations, and then solve them together to get c and b. First, I plug in -1, 6. I get 6 equals c times b to the -1, or c equals 6b. Then I plug in -3, 24. I get 24 equals c times b to the -3rd, or c equals 24b to the 3rd. Set these two things equal to each other to get rid of the c. So 6b equals 24b cubed. And then solve that all together. Move everything to one side and factor. B has to be positive, so I'm going to throw out the negative answer on that. Overall, I just get b is 1/2. And if b is 1/2, by using either one of those two equations by the arrows there, I get that c has to be 3. Plugging in those values, I get a final answer that f of x is going to be 3 times 1/2 to the x.